All right, welcome to this explainer. Today we're diving into integral calculus, and we're going to demystify the whole thing by treating it like a massive, exciting exercise in reverse engineering. Now look, I know what you might be thinking. If you've ever felt a wave of pure panic just looking at those terrifying stretched out S symbols in a math textbook, well, you are definitely in the right place. We are going to break down exactly how to read them, how to actually use them, and honestly, why they're one of the most powerful, practical tools in all of applied math.
Let's kick things off with a real-world problem that proves exactly why we need to learn how to reverse a mathematical rate of change. Imagine you're looking at a business, right? You don't have their total cost spreadsheet, but you do know precisely how fast their costs are changing with every single new unit they produce. So here's the big question. If you only have that rate of change, can you somehow build back the original picture and figure out their exact total cost?
Section 1. Reverse Engineering Calculus. The concept of undoing.
To solve problems like that business scenario we just talked about, we really need to master the mathematical art of undoing. Okay, let's dive into this comparison. You see, we already know how to break functions down to find their rate of change using differentiation. You take a function, you differentiate it, and boom, you get a derivative that tells you the slope. But what if we're already holding the derivative and we want to find the original function? Well, that is exactly where integration, or anti-differentiation, comes in. It's literally the exact reverse process. You're taking the rate of change and building that original function right back up.
Let's quickly lay out the jargon we'll be using here. When you look at an integration problem, you're going to see that tall, stretched out S. That is the integral sign. The function sitting right next to it, the actual thing we want to reverse, is called the integrand. And finally, there is the letter C, which is known as the constant of integration. We're actually going to spend quite a bit of time on this C because, well, it's the absolute key to making this whole system work.
Section 2. The mystery constant C. Hunting the mathematical ghost.
All right, so we have to talk about the absolute biggest stumbling block for beginners. Why in the world do we always have to add this mystery letter C to the end of our answers? Well, think about it. Because any constant, like just a plain old number 5 or -7, disappears completely when we take a derivative. Integrating leaves us with this sort of mathematical ghost. We know a constant might have been there originally, but its value was totally wiped out when the derivative was taken. So when we integrate, we add C to represent an infinite family of parallel curves. As you'll see on this graph, functions like 2x plus 5, 2x minus 3, and 2x minus 7, they all have the exact same slope, which means they have the exact same derivative. So without knowing C, we don't just have one single curve, we have an entire parallel family of them.
But hey, the good news is we can trap this mathematical ghost and find the exact curve, provided we're given what's called an initial or boundary condition. Basically, this means if we're given just one exact data point to plug in, like say knowing that when x equals 3, y equals 11, we can actually solve for C. Once we plug those numbers in, C is no longer a mystery. We've successfully singled out our one specific curve from that huge infinite parallel family.
Section 3. The Essential Integration Toolkit, Reversing the Rules.
Okay, let's rapidly build out the core toolkit we need to actually do the math here. Here's a breakdown of the first 6 rules. And notice how they perfectly mirror the rules of differentiation, just in reverse. Now, what's really crucial here is rule number 3, the power rule. To integrate a power function like x squared, you simply add 1 to the exponent and then divide by that new number. So x squared just becomes 1/3 x cubed. Super simple. We also see some special cases, like Rule 4 for x to the -1, which integrates into the natural logarithm of x. And, just as a fun bit of math trivia, Rules 5 and 6 show us that exponential functions, especially those with the base e, are incredibly resilient. They often just integrate right back into themselves, simply divided by their constant.
And brilliantly, Rules 7 through 9 tell us that we can factor out constants and easily split up sums and differences. So if you have a really long polynomial with a bunch of terms added together, Rule 8 says you can just integrate each piece individually. And Rule 7 says if there's a constant multiplier in your way, you can literally just pull it right outside the integral sign, do the integration, and then multiply it back in at the end. These rules are absolute lifesavers because they keep complex equations completely manageable.
Section 4. Advanced Integration Tactics. Clever hacks for complex math.
But what happens when our basic toolkit completely fails against a complicated product or quotient of two functions? Because let's face it, the real world rarely gives us perfectly simple equations. Well, when we hit a wall, we use a clever hack called integration by substitution. This essentially reverses the chain rule in 4 precise steps. First, you spot the most complex part of the integrand, usually the function raised to the higher power, and you simply swap it out for the letter u. Next, you take the derivative of that u. Third, you use a little algebra to solve for dx. And finally, you substitute u and du right back into the original problem. Suddenly, this massive, ugly equation collapses into a simple, single variable that you can integrate super easily using the basic power rule. Once you're done, you just swap the original variables back in. It is, quite honestly, pure mathematical magic.
But wait, what if substitution doesn't work? What if you have a variable multiple that just will not cancel out? If substitution fails, we rely on a backup technique called integration by parts. Now, instead of memorizing a messy textbook formula, the really crucial point here is understanding the concept. This technique relies on splitting your ugly equation into 2 distinct parts. You deliberately pick a simple piece of your equation to differentiate, and a more complex piece to integrate. By doing this, you're systematically breaking the problem down into smaller, bite-sized pieces until it's finally solvable.
Section 5. Real-world economic applications. Why it matters.
So what is the point of all this abstract math anyway? How does it actually solve that business problem we posed at the very beginning of this explainer? Well, let's look back at economics. In business, marginal cost is the incremental change in total cost from producing just one more unit of output. It is literally a rate of change. It's a derivative. So if a business only knows their marginal cost, they can use integration to reveal their total cost. By integrating the marginal cost function, they get the total variable cost. And hey, remember that mystery constant of integration, C, that we talked about earlier? In this exact scenario, C is exactly equal to the company's fixed initial costs. It's amazing. It all ties together beautifully.
And it works on a macro level too. On a macroeconomic scale, economists look at net investment. Net investment is defined as the continuous rate of change in capital stock over time. So by taking that rate of investment and integrating it with respect to time, economists can accurately estimate a whole nation's total level of capital stock. The starting capital at time 0 basically acts as our boundary condition, which successfully traps our mathematical ghost, perfectly solving for C, and giving us an exact, concrete formula for the entire country's economic growth.
This kind of analysis, tracing the time path of variables, is called economic dynamics, and it leaves us with a really fascinating question to ponder as we wrap up this explainer. Think about it. If we can trace the continuous time path of these massive, complex variables just by integrating their rates of change, can calculus actually predict the exact moment a volatile shifting market will finally settle into equilibrium? It is definitely something to think about the next time you see a market trend line changing. Thank you so much for joining me on this explainer, and as always, keep questioning the data.